So hi everyone. So I'm going to talk to you about the hydrodynamics of cuttlefish jet propulsion. So cuttlefish swim using a dual mode locomotive system. So this consists of undulations of the fin, which animals typically use for fine manoeuvres and during slow swimming, and jet propulsion swimming, which is used across the speed range and is the exclusive mode during escape. So cuttlefish can use these modes both independently and together, and this gives animals locomotive flexibility. So in swimming by jet propulsion, animals use the muscles of the mantle cavity. So these are the circular and radial muscles. So the circular muscles act to compress the mantle cavity, which forces water out through the siphon. So this water forms a structure which we call a jet vortex. So I did have an image here of showing that, but it's not showing up. So this structure, basically you get like a donut shape with water flowing around it and through the centre. So these jet vortices act to create thrust, which is important in moving animals forward. So jet propulsion is often considered to be an inefficient mode of swimming, particularly when you compare it to the swimming of fish, which is undulatory swimming. So this is because you propel a small volume of water at high velocity, whereas during undulatory swimming you propel a large volume of water at a lower velocity. So this creates the same level of thrust, so you don't have to use as much mechanical energy to do this. So this shows the importance of thrust. So we use formation numbers to describe jet structure. So these describe the relationship between jet length and diameter, and previous work with mechanically generated jets has shown that between 3.6 and 4.5, this produces the highest per pulse thrust. So this is considered the optimal range for producing a jet. So above this structure, the jet structure begins to break down, and you get this lower image shows it a more elongated jet. So this occurs when a lot of energy is put into a jet in a short amount of time. So such as if an animal is trying to escape. But this is less efficient to do this than it would be to just produce one isolated jet. So in carrying out these experiments, we wanted to answer three key hypotheses. So we thought cuttlefish would try to optimise their thrust production per jet, so we expected them to produce formation numbers around this 4 mark. We also thought cuttlefish would try to maximise their hydrodynamic efficiency. So we thought that cuttlefish efficiency would fall between that of nautilus and squid. So we thought this because of the intermediate morphology of the cuttlefish, where they've retained the cuttle bone, so they can't expel as much water per jet event, but they're not as restricted as the nautilus with the large external shell. We also thought hydrodynamic efficiency would decrease with animal size. So previous work looking at squid paralarvae and as squid develop has found that you get this decline in the efficiency of the jets as they get larger in size. So to carry out this study, we used 36 cuttlefish, and we used 2 ages. So we had 19 hatchlings, which were all less than 5 days old when we carried out the experiments, and we had 17 juveniles, which were all around 2 months old when we carried out these experiments. So to carry out these experiments, we used a method called particle image velometry. So this basically involves us seeding a tank with a reflective particle, so we use aluminium oxide particles, and then we illuminated this using a 1mm laser light sheet, and we recorded the movement of the cuttlefish through this at 500 frames a second, and this allowed us to track the movement of these particles, which allowed us to look at the jet structure, such as the jet velocity, vorticities of that flow around that donut structure, as well as how quickly the animals are moving and the structure of the jet itself. So in carrying this out, we found that the cuttlefish did produce two types of jets. So these are the isolated jets and these elongated jet structures. So these diagrams here, we've got the donut structure there describing where we're taking measurements from. So because we only had a 1mm light sheet, we only get a section through the centre of it. So we get the velocity, which is the bit going right through the middle, so that's the images closest to myself, and the vorticity, which is the flow around this structure, which are the images on the other side of the room. So our first question we want to know is thrust optimised per jet event? So we found that animals were producing formation numbers in that 4 mark. So this suggests that this is optimal thrust that they are producing. And then we wanted to look at the 2 jet types, and we found that the formation numbers differed significantly, but this didn't translate to any differences in thrust, hydrodynamic efficiency, or even the animal swim speed. So we next want to know how efficiently jet energy is transferred into momentum. So we found that hydrodynamic efficiency was strongly influenced by developmental stage, where the hatchlings were significantly more efficient in transferring this energy into momentum than the juveniles. We also found that hydrodynamic efficiency increased with swim speed. So you can see that on this top diagram there, that this was a logarithmic relationship we found. So, in terms of thrust production, the formation numbers suggest that this is optimal, and jet type didn't seem to significantly impact upon this. So this suggests that cuttlefish can optimise thrust production regardless of the structure of the jet itself. So then we want to look at where cuttlefish fit with the rest of the animals. So we found that cuttlefish hydrodynamic efficiency falls between that of nautilus and squid. So on this diagram, cuttlefish are displayed in orange. We also found, when I went to look at all this data, that the efficiency of cephalopods was higher than most of the other jet-propelled animals. So I've highlighted the salps here, which are often considered to be the most efficient of jet propellers because they jet propel quite differently to how most animals do. So they take water in and it kind of just goes straight through the 2 openings. So we also found that there was a nice overlap between the fish and cephalopods, which suggests that cephalopods can match the efficiency of fish if they want to. But this was particularly true at higher swim speeds. So they had to be at a high swim speed anyway to start to match this efficiency. So the implications of this work, so the efficient use of energy is key to animal survival. So in maximising the thrust per pulse, cuttlefish can maximise their efficiency. So this means that they don't have to jet as often using the mechanical energy. So this means that animals can invest energy that would be put into an inefficient system elsewhere, such as growth and reproduction, which is probably important for cuttlefish. So to summarise, we found that cuttlefish produce 2 jet types, so these single isolated jets and elongated jets. The structure of cuttlefish jets is optimal for thrust production, but jet types don't seem to differ in thrust efficiency or animal swim speed. We found that hydrodynamic efficiency increased with swim speed but declined with age. And we found that this efficiency fell between that of other cephalopod lineages. So I'd like to thank everyone who supplied us with Cuttlefish X to do this research. Some of my colleagues at the University of Leeds who helped a lot with animal maintenance and some of the data collection. I'd also like to thank SEB and the Company of Biologists and the University of Leeds who all provided funding for parts of this project or travel. So thank you for listening, and I welcome any questions.